Welcome to a proof of Chaudoin's theorem. Chaudoin's theorem states that any function f of t is equal to that function flipped upside down. We will be proving this using fancy notation, reckless assumption, and insufficient testing. First, let's cover the theorems and formulas needed for this proof. Hunky-Rhine's substitution rule states that any variable can be swapped for any other variable at any point. Similarly, Lewton's axiom of universal variable usage states that if a variable is found to have a value in one situation or problem, it can be assumed that that variable will have the same value in any situation or problem. Helen Keller's axiom states that if something looks like something else, they may be used interchangeably. Chaudoin's theorem states that, given some fractional function f of t is equal to the corresponding Chaudoin matrix, which looks like this. Chaudoin's theorem states that, given some piecewise function p of t is equal to the determinant of the corresponding Chaudoin matrix. Chaudoin's theorem assumes that we are ignorant non-calculus students and lets the nth derivative of y equal y to the n. Newcomb's theorem states that n factorial times the nth derivative of y is equal to 1. Phile's law of infinite summation states that the sum of all natural numbers is equal to negative 1 over 12. Finally, the Nech function, Nech of x, is defined as the integral from 0 to x of t factorial with respect to t, which is equal to the integral from 0 to x of the gamma function of t plus 1 with respect to t. Now, let's begin. We will be proving that gamma of n plus 1 is equal to the Laplace transformation of u plus 1, where u is the function n upside down. Using insufficient testing, we will use this to prove that any function is equal to itself upside down. First, we use Hunky-Rhine's substitution rule to replace n with y. This means that u will also be replaced with lambda, which is y upside down. Taking the Laplace transformation of lambda plus 1, we get 1 over s squared plus 1 over s, and by Chaudoin's theorem, we can rewrite this as a Chaudoin matrix. Now, to find the eigenvalue of the Chaudoin matrix, which will be lambda, we can use Helen Keller's axiom to replace s with 5 since they look similar, giving us this. This shows that the eigenvalue is 3 plus or minus the square root of 29. Plugging the eigenvalue back into the Laplace transformation in place of lambda, we get the Laplace transformation of 4 plus or minus square root of 29, which is equal to 4 plus or minus the square root of 29 over s, and using Helen Keller's axiom once again, we can say that this is equal to 4 plus or minus 29 over 5. Since we've now found the value of f upside down, let's find the original function. Let f of y equal gamma of y plus 1 and g of y equal 1. Using the convolution formula and plugging in f of y and g of y, we can see that gamma of y plus 1 convolute 1 is equal to this, which, if we recall, is just the Nech function. Now, as you can see, the Laplace transformation of f convolute 1 is just f of s over s. But since Chaudoin's theorem states that we're non-calc students, we probably don't know what a Laplace transformation is, so we can just ignore the Laplace part. Since f convolute 1 equals Nech of y now, that means that f of s over s is also equal to Nech of y. Therefore, f of s equals s times Nech of y. And Nech of y is equal to the Laplace transformation of gamma of y plus 1. Now let p of s equal Nech of y. Since the Laplace transformation of gamma of y plus 1 is equal to s times p of s, gamma of y plus 1 is equal to the inverse Laplace transformation of s times p of s, which is equal to the derivative of the delta function of y convolute the inverse Laplace transformation of Nech of y. By the definition of the Laplace transformation, p of s is also equal to the integral from 0 to infinity of e to the negative sy times p of y with respect to y. Therefore, the gamma function of y plus 1 is equal to e to the negative sy times p of y. We can use this to show that p of y is equal to e to the sy times gamma of y plus 1, which is equal to the inverse Laplace transformation of Nech of y. Now we can plug this back into the formula for gamma of y plus 1 to find that gamma of y plus 1 is equal to the delta prime function of y convolute e to the sy times gamma of y plus 1. We can use Helen Keller's axiom to find that convolution is the same thing as multiplication, since the two symbols look very similar, which means that 1 is equal to the derivative of the delta function of y times e to the sy. By Chaudoin's theorem, we can see that e to the sy is equal to e to the s, and then the yth derivative of e. Therefore, 1 is equal to the derivative of the delta function of y times e to the s, the yth derivative of e. And by Lucum's theorem, this means that the derivative of the delta function of y is equal to s times y prime, since the coefficient of e to the s, yth derivative of e, must be s times y factorial. With algebraic manipulation, we can see that y factorial is equal to the derivative of the delta function of y over s, which, as you know, is just equal to the gamma function. Once again, using Helen Keller's axiom to show that s is equal to 5, we can find that the gamma function of y plus 1 is equal to 1/5 of the derivative of the delta function of y. And by Chaudoin's theorem, the derivative of the delta function of y can be rewritten to just be the delta function of y. Using the definition of the delta function, delta y is equal to this. Infinity is equal to aleph null, which is equal to the sum of all natural numbers. Using number Phile's law of infinite summation, we can find that infinity is equal to -1/12. So we can replace infinity in the delta function with -1/12. Using Chaudoin's theorem and letting x and n equal 0, we can find that 0 to the 0 is equal to the 0th derivative of 0, therefore showing that 1 is equal to 0, and that -1/12 is equal to 4 plus or minus root 29. Therefore, we can replace -1/12 with 4 plus or minus square root of 29 in the piecewise function. The piecewise function is equal to 0 when y is not equal to 0. Therefore, we can just take some arbitrary value where y is not equal to 0, like y equals 1, and just put it in the function. Now we can use Chaudoin's theorem to transform this piecewise function into the determinant of the Chaudoin matrix, which gives 4 plus or minus root 29. Now, since this piecewise is the delta function, this shows that the delta function is equal to 4 plus or minus the square root of 29. And since gamma of y plus 1 is equal to 1/5 of the delta function in this case, this means that gamma of y plus 1 is 4 plus or minus the square root of 29 over 5, which, if you recall, is the same thing as the Laplace transformation of lambda plus 1. Therefore, they are the same thing, and using insufficient testing, we can show that this theorem applies for any function f of t.